Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on residuals and computer output. Regression is a technique that fits a model as close as possible between all of the coordinates of the variables. A regression line is a straight line used to predict the value of y for a given x. The residual, denoted with the lowercase s, is the difference between the actual value of the response variable and the value predicted by the regression line. So it is the vertical distance or vertical displacement. And here's our formula for residuals. You take the actual or observed value of y, and you subtract the predicted value of y hat. Now, on your test, I want you to show the formula, show your work, and include units. Unexplained numbers on the AP Stats exam are ignored, so show your work and include units. So here I have 4 points, and I fitted the blue line there. What I want to say here is that points that are above the line have positive residuals, and points that are below the line have negative residuals. So let's look at that lowest point there. Here, a negative residual indicates that the actual y value is less than the model would predict. That is, the model overestimated the value of y. So how do we calculate, how do we determine the actual regression line? Here's the explanation. The least squares regression line is the line that minimizes the sum of the squared vertical distances between the data points and the line. So it's the line that minimizes the sum of the squared residuals. So here I have 3 points, and I want to fit a line between them. So I find the line that minimizes the sum of d1 squared plus d2 squared plus d3 squared. And that is my least squared regression line. Outliers. Let's talk about outliers. Regression is sensitive to outliers. It is not resistant to the influence of outliers. An outlier that has an x value close to the mean will not change the slope very much, but could move the intercept higher and lower depending upon if the outlier is above or below the line. Actually, we have 3 vocabulary words to learn here. So an outlier is a regression point that does not follow the general trend shown in the rest of the data and has a large residual when the least squares regression line is calculated. So an outlier has a large residual. A high leverage point in a regression has a substantially larger or smaller x value than the other observations. So we have an extreme value from the perspective of x values. An influential point in a regression is any point that, if removed, changes the relationship substantially. Examples of relationships that could be changed include having a different slope, having a different y-intercept, and or having a different correlation. Outliers and high leverage points are often influential. So I want to talk about this scatter plot up there at the very top. It is a scatter plot of height and weight. And let's talk first about the red dot right there, the red dot. Suppose that the red dot is a sumo wrestler, a person who is very heavy but of average height. And the question is this an outlier? Is it a high leverage point? Is it an influential point? Well, it is an outlier because it has a large residual and is outside the trend. It is not a high leverage point because the x value is close to the mean of the x's. And it is an influential point because its presence tends to increase the y-intercept. and also its presence tends to decrease the correlation coefficient. So now let's look at the green dot. Imagine that the green dot is Shaquille O'Neal, a very big basketball player. Now Shaq is an outlier in terms of height and an outlier in terms of weight, but is not an outlier with respect to the relationship between height and weight. You know, Shaq is right on the regression line. So not an outlier with respect to the relationship between height and weight. Now, so Shaq, that green point, is not an outlier in the regression because it is along the trend and has a small residual. It is a high leverage point because it has an extreme X value. And it is an influential point because its presence tends to increase the correlation coefficient and will often affect the slope. So that's how you take 2 points like that and analyze whether they're outliers, high leverage points, or influential points. So this is what computer outputs look like when you do a regression analysis. It will give you the predictors and their coefficients. So we're going to talk about that here. One of the things we can ask you to do is to write the equation for the regression line. So with this data, I would say that the regression line is y hat is equal to my intercept term, that is 17.25, minus 0.0669, that's my slope coefficient, times my explanatory variable, odometer. So that's how you would write the equation with this data right here. Now let's talk a little bit about S. This is the standard error S. It's different from residuals. This is the standard error S. And that value is 0.3265. It is considered as the standard deviation of all of the residuals. It is interpreted as the typical amount of variation in the dependent variable for a given X. That's important. It's interpreted as the typical amount of variation in the dependent variable for a given X. And I want to explain that. So the standard error is the standard deviation of the residuals. It is interpreted as the amount of variation in the dependent variable for a given X. It is the typical amount of variability in the vertical distance from the observed Y to the regression Y. And so this cross-section here on this graph on the right is showing you that if we take a cross-section for any given X, you will see that the residuals are normally distributed around the regression line, around the predicted value for Y. A residual plot is a scatter plot of the residuals against the explanatory variable. Residual plots are important because they help us determine whether the model that we are using is appropriate. This graph right here, this slide right here, shows you the relationship between the observed data and the residual plot. So on the left here, I have my scatter plot, and the dotted line is my regression equation, my regression line. And let me just show, and on the right-hand side here, I have the residual plot. Now, the residual plot always has the same x-axis as the original data. But it's basically what we're doing here is we're going to turn tilt that regression line so that it becomes a horizontal line. So you see these 2 points right here at the bottom of my scatter plot here. These are below the regression line, so they correspond with these 2 points right here on my scatter plot. These 2 points are below the regression line and have the same residual, the same vertical distance from the regression line. And up here I have 3 more points. This is in my sample data, my scatter plot. And these 3 points have decreasing residuals, and they correspond to these 3 points up here in my residual plot. So this is the residual plot on the right that corresponds with my scatter plot on the left. When we do a regression, we want to analyze how well the data fits, how well our model fits the data. Sometimes this is referred to as a goodness of fit analysis. So before we use the coefficients of the least squares line for prediction, we need to assess the model to see how well it fits our data. And I'll show you two things that we do to assess the goodness of fit. First thing we do is we look at the residual plot. So the residual plot is a plot of the residuals versus X. And what we're looking for here is patterns. In A, the residual plot on the left, the residual plot appears randomly scattered above and below the regression line, and there's no pattern. This is what we want to see. We want to see a random scatter of the residual plots. This indicates that our explanatory variable is extracting all of the signal possible, and it confirms that our linear model is appropriate. Now, if you see a residual plot like the one on the right, then you've got some work to do. In the residual plot on the right, the residuals are not independent. They have a curved pattern, so our linear model is not correct. We probably need to change the model a little bit so that we can take out that curve in our residuals. Another thing we do to check the goodness of fit is to look at the coefficient of determination R squared. And this is interpreted as the fraction of the variation in the values of Y that is explained by my least squared regression equation. Another way of interpreting it is that R squared is the percent reduction in the sum of squared residuals when using the linear model to predict outcomes as compared to using the mean of Y to predict outcomes. So those are two interpretations of our coefficient of determination R squared. Now let's practice that. If R squared is equal to 0.6483, then here's how we interpret it. About 65% of the variation in Y is accounted for by the linear relationship with X as the explanatory variable. But of course, you're going to have to do it in context. So in your interpretation, you should refer to the context of the problem. That is, you're going to replace the reference to Y with a reference to the dependent variable in the problem. So if 65% of the variation in Y is explained by my linear relationship, that means I have 35% unexplained, and that might be just due to random error, or I might be missing some explanatory variables, something like that. What is the relationship between my coefficient of determination R squared and my correlation coefficient R? When there is only one independent variable, the absolute value of R is equal to the square root of R squared. So we might give you the R squared. The computer outcome output would generate the R squared. Let me just go back and see here. Here's my R squared right here, 0.6483. That was my R squared for this problem. Okay, so we give you the R squared and we ask you to calculate the coefficient of correlation coefficient R. And so we take the square root, but now we still have to decide, does R have a positive sign or a negative sign? And it always takes the same sign as the slope coefficient. Facts about R squared. R squared ranges between 0 and 1, and R squared of 1 means that all of the points lie exactly on the line. When R squared is high, we say that the fit of the model is good. When R squared is low, we better look for further explanatory variables that can help capture some of that unexplained variation. Now, here is another technique for calculating the regression equation. And what happens here in this type of problem, we are going to give you, the problem will give you all of these statistics. It will give you the correlation coefficient. It'll give you the standard deviation of the Y variable, the standard deviation of the X variable, and it will tell you the average Y and the average X variable. And then what it'll do, it'll ask you to calculate the equation for the line. There's really not much here I have to teach you because these formulas for A and B, the slope coefficient and the intercept, are on your formula sheet. So when you see a problem like this, it's just a matter of plugging numbers into the formula and writing out your equation. These formulas allow us to calculate the linear regression equation using only the means and standard deviations of the two variables and their correlation. So if you see all that kind of data in the problem, then likely you're going to have to use these formulas, dig out your formula sheet, plug the numbers into the formula, and write out the equation. Fun facts about regression: prediction outside the range of available data is called extrapolation, and we want to avoid it. It's risky. Regression coefficients are not resistant, that is, they are strongly affected by outliers. The least squared regression line always passes through the point where x is equal to the mean of x and y is equal to the mean of y. And switching the values of x and y does affect the least squares regression line, because my least squares regression line minimizes the sum of the squared vertical distances from the line. So let's work through a problem here. This is the kind of thing that you might expect to see on problems in this unit. Here I have given you the regression output for this regression. It's the output for regression of crop yield, that's my y variable, in thousands of bushels, on annual rainfall, x in inches, over the last 12 years at some farm. So first thing we might ask you to do is write the equation for the regression line. I know my intercept is 6, I know my slope coefficient is 14, and my explanatory variable is rainfall. So I write this, crop yield with a hat on it. So my predicted crop yield is equal to 6 plus 14 times rainfall. I'd rather have you write it like this, rather than saying y hat is equal to 6 plus 14 times x. This way, by adding the names of the variables, I've added context. Identify and interpret the slope coefficient. So my slope coefficient is 14, b is 14, and here's how I interpret it. When the annual rainfall increases by 1 inch, the predicted crop yield increases by 14,000 bushels on average. And having the word predicted or on average is critical to your answer here. There's my least squares regression line. We may ask you this type of question. What is the predicted crop yield when the annual rainfall is 20 inches? So we're just going to plug 20 in for where you see the word rainfall, and I get my predicted crop yield equal to 286,000 bushels. Please include units. The next question is calculate and interpret the residual when the annual rainfall was 20 inches and the crop yield was 275,000 bushels. Well, we're asking for the residual when the annual rainfall was 20 inches, and I already know what the predicted value was. I just calculated that above. So I use my formula. The residual is always the actual crop yield minus the predicted crop yield when rainfall was 20. So I take 275, my actual, minus 286, my predicted, and I get 11,000 bushels. We have a deficit of 11,000 bushels of negative residual. So what does that mean? We have to interpret it. So here's how I interpret it. The actual crop yield was 11,000 bushels less than predicted. Okay, so we can ask you to interpret r squared. So here we have my r squared, and that's equal to 0.92. And the interpretation is this: about 92% of the variation in crop yield is explained by the linear regression with annual rainfall as the explanatory variable. Then we can ask you to calculate and interpret the correlation coefficient, r. So we know that there's a relationship, the correlation coefficient. The absolute value of the correlation coefficient is equal to the square root of r squared. So I take the square root of 0.92 and I get 0.96, but I still have to figure out whether it's going to be positive 0.96 or negative 0.96. I look at the sign of my slope coefficient. It's positive, so my r is positive 0.96. Now I have to interpret it. So we're going to say that there is a strong positive association between annual rainfall and crop yield. One last question. Here is the graph of the residuals. So we've done our residual plot. We've got our residual plot right here. And the question is this: is the linear model that we calculated a good fit for the data? Well, we have a high r squared, so that's a good sign. and we see no pattern. The residual plot just shows a random scattering of data above and below the line. So we're going to say yes, the linear model is good. The residual plot looks randomly scattered about the residual line equals 0 and shows no pattern. So the linear model is a good fit. So thank you very much for listening to this presentation.